evaporator and the condenser, they are both closed style heat exchangers, right? Two flows, they are separate. And for the condenser, one flow is the refrigerator and refrigerant. The other flow is not inside the condenser, it's just atmospheric air. Okay, so the heat is rejected by the refrigerant to the atmospheric air. And the evaporator, one flow is the refrigerant, the other flow is air inside the refrigerator. So the heat is transferred from the air inside the refrigerator to the refrigerant. Okay. And compressor, actually there are many types of compressor. So we have postgraduate subjects I've been teaching since 1997, just called air conditioning. So if you are working in air conditioning industry and you are interested in learning something more theoretical, actually it's not too theoretical, it's still application like thermodynamics, and you can do that subjects. Air conditioning is not offered this semester, normally offered in autumn semester, but not this semester because the new lab is not ready in building this building and level 10. But will be offered next year. Okay, that's the cycle described on the PV diagram, but basically we will look at TS diagram or even TH diagram. Okay, so constant entropy we can see as isentropic compression followed by a reversible constant pressure heat rejection process in the condenser, and followed by that's the idealized. Actually, it's not like that. Idealized. Another isentropic expansion process, and then followed by evaporation process, constant pressure. But actually, this part is irreversible. Okay. So corresponding to the four devices in the refrigerator, here we can see the cycle. Okay, described by 1 to 2, 2 to 3, 3 to 4, 4 to 1. Okay. The other cycle 1 prime to 2 prime to 3 to 4 prime back to 1 prime. What's this cycle? From the shape, can we recognize what's this cycle? 1 prime, 2 prime, 3, 4 prime, back to 1 prime. Yes, but we've forgotten the name, have we? Carnot cycle, right? Carnot cycle is the most efficient cycle, okay, with the same reservoirs. Okay, if the conditions are the same, with the same condenser, the same evaporator, Carnot cycle is the most efficient cycle. But we have seen why, many reasons why Carnot cycle can't be directly applied. Okay. So from this idealized refrigeration cycle, first we look at the process 1 to 2. That's the process happening in the compressor. Okay, it's an isentropic, reversible, and a diabatic compression process. So on the TS diagram, we can see it's a straight line vertical to the entropy axis. Okay, because entropy change is 0. Okay, reversible and diabatic. And then it's followed by a reversible constant pressure heat rejection process. The heat is rejected from the refrigerant to another flow. In the domestic case, it's rejected to the atmospheric air. But for large air conditioning system like the air conditioning system at UDS, air is not enough. So we need cooling water, okay, to take the heat away. So in a large air conditioning system, the condenser, okay, in the condenser, the two flows, one is refrigerant, the other one is cooling water. Okay. And then followed by the process in the expansion valve or capillary tube. I mean the very tiny tube to generate enough frictionals and to drop the pressure from the condenser pressure to the evaporator pressure. Okay, and why do we need low pressure inside the refrigerator? We need the refrigerant to evaporate at the meantime to take the heat away, right? And the low pressure that's happening in the saturation region. We know inside the saturation region, pressure and the temperature, they are dependent, right? They are called saturation pressure and the saturation temperature. We need low temperature for the refrigerant to evaporate, right? And correspondingly, the saturation pressure is low. Okay, that's why we need a low pressure. Now we understand why we need to drop the pressure here, and then 4 to 1 is the evaporation process. It's constant, reversible constant pressure evaporation process happening in the evaporator. Okay, so that's the 4 process. And if we go back to your study guide, that's what I need to mention about. Okay, so that's the page in your study guide, the blue book. Okay, so it explains the 4 processes corresponding to these 4 devices described by words. Okay, that's what I just said. Okay, here, did you have this in your study guide? That's very, very wrong. That's my mistake. So failure. That's a failure, yeah. I don't know how this can be here. Probably I copied it from like a Brighton cycle because the application, the formula is the same. Okay? So that's for ideal gas. That's for ideal gas in the isentropic process. Remember I said many times there are 3 equations like that to describe the relation between the properties of ideal gas. And I said many, many times, yeah, I hope it's not too trivial to you, to apply, to use this equation, to use equation like that, 2 conditions must be met. What are these 2 conditions? First, ideal gas, right? Must be ideal gas. Second, must be isentropic process. Okay? So even this is isentropic compression process because we are not sure, especially state 1. Maybe state 2 can be close to ideal gas, but not state 1. Okay? So at least in these subjects, don't use this formula for the refrigerant. Okay? Don't use this formula for the refrigerant. And for for isentropic compression process, I'm not going to start again, from the general equation for open system and simplify to steady state, steady flow process, and simplified because there is only single flow stream, and further simplified by ignoring the kinetic energy, potential energy, and also isentropic means reversible and adiabatic. So the Q is not here. Okay, is that all right? Okay, only one person agreed. Yeah. Do you think you can get to this equation from the very general, the original general energy equation when the first law applied to steady state, steady flow processes? Okay, that's good. Because all these 4 processes, they are steady state, steady flow process. Okay, and happened steady state, steady flow process must be in open system. Okay. So application of the first law, application of the second law. Big cross for this one. And then followed by the process in the condenser, reversible heat, reversible constant pressure heat rejection. We can see that's along a constant pressure line, okay? And in a real condenser, the pressure should be slightly dropped because of the friction loss in the pipe. But here, because it's a reversible process, so any energy loss is just zero. And again, that's from the application of the first law to this heat rejection process. Okay, because for any heat exchanges, there is no moving boundary. Okay, and also the kinetic energy change shouldn't be very significant, and then no potential energy change. Okay, so that's the QH. Please notice here QH. Remember, for refrigerator and the heat pump, the heat is transferred from the low temperature reservoir to the high temperature reservoir, right? So that's why to the high temperature reservoir is rejection. But this wouldn't happen automatically. It's because there is the energy input. That's the electricity to drive the compressor. Okay? So the second type of statement, or the second law, means it's impossible to develop a refrigerator or heat pump without electricity feed. That's my interpretation. It means we must pay for the energy input to operate a refrigerator or heat pump. And then process in the expansion valve. Okay, so that's a throttling process, and we already record as a constant enthalpy process. Okay, constant enthalpy process, that's quite common in refrigeration systems. Okay. And then the last one, that's the process actually, that's what we need. Okay, 4 to 1 to take the heat away. So that's a heat addition process. Heat is added to the refrigerant. Heat is transferred from the surrounding air, the air inside the refrigerator, to the refrigerant. Okay, so it's positive. Okay, that's still application of the first law. And coefficient of performance, I didn't use beta because in your textbook, beta is used to denote the coefficient of performance. So coefficient of performance of the refrigerator is what we need divided by what we pay for. Okay? So what we need is the heat taken by the refrigerant in the evaporation process and divided by the power to drive the compressor. Okay, and there is another diagram I just copied from somewhere, because if you have worked in industry for air conditioner or refrigerators, you must have seen this. Okay, industry doesn't use very much TS diagram. Mainly they use the pH diagram, and also there is a pH chart before we have the software. Okay, and so pH diagram just means mainly for the throttling process. Okay, that's constant enthalpy process. Okay. So that's the corresponding pH diagram to this TS diagram. Okay, so that's the what we need to understand by applying the first law, second law to analyzing this refrigeration cycle. So next we are going to see some examples. So for people, just make sure everyone cross this. Okay, don't be confused. We have used this guide for many years, and I used to write down all the equations in the past. No one has found this mistake, because I don't have this in the PowerPoint, so that's why I need the study guide. Probably people don't read this; they only look at the questions. That's not very helpful in this subject. In some of the subjects, maybe with more examples you can understand more. But in thermodynamics, we must understand the theories, the concepts, okay? And before we, look at the questions. If you can remember the solutions for one or two, or even many questions, I'm not sure if the question in the final exam, will be exactly the same as questions you have memorized the solutions. So master the methods, okay, understanding the concepts. I think that's the most important thing. Okay. The final exam questions, from what you can see, won't be hard at all. You wouldn't find anything surprising you, not like that. Okay. In some of the subjects I've heard, the questions the students never seen before, but these questions probably you have never seen before as well, exactly the same. But you will find that they are very similar to what we have done. It's for I think the exams, there's opportunities for us to revise, to enhance our learning. So if you think in that way, you wouldn't feel too nervous. Okay, then we just go to the questions. And just again, the feedback survey will be closed on the 6th. So that's what I just received another email